Hi, it's Matt, and in this video we're going to talk about the third postulate of quantum mechanics. So let's talk about what the third postulate says. It says that the only possible values we'll call omega that can be measured for an observable with corresponding operator omega hat are those satisfying the eigenvalue relationship given here, which is that our operator, so omega with the symbol over it, applied to a function, is going to be equal to a constant omega times that same function. And these values we call the eigenvalues of the operator. So again, this is our operator, this is our eigenvalue. And then we'll talk a little bit about what we call our function. So again, here's that same relationship. We have an operator applied to a function, and that's going to be equal to a constant times that same function. So let's talk a little bit more about this. We first have our operator. So in general, an operator is a mathematical instruction, and in quantum mechanics, we know that linear and Hermitian operators correspond to a physical observable. What I have here is just a short version of what we're told by the second postulate of quantum mechanics. Now, new to us is the idea of an eigenfunction, which are shown here by the lowercase phi. So an eigenfunction is a function corresponding to a particular operator that allows the above relationship to be true, or in other words, we could find such a lowercase omega shown in green that makes this relationship true. But it should be noted that a single operator can have multiple eigenfunctions. And finally, in green, we have our eigenvalue. An eigenvalue is a unique constant. So again, unique meaning for a particular eigenfunction and operator, there only exists one eigenvalue. And constant meaning it cannot depend on a variable. It must be a fixed value. So let's talk a little bit more about this. So here are a few key notes we should mention. The eigenvalues are the only values that can be measured for a particular observable, physical observable, I should say. And in the eigenvalue relationship, the eigenvalue again must be constant, not a function of any variables such as position or momentum. It should only depend on other constants or numerics such as 2 or 3. Also, if an operator has multiple eigenfunctions, these functions can be differentiated by the subscript k, such as in phi k, where again, k is a particular constant that corresponds to each eigenfunction. Similarly, the eigenvalue for the kth eigenfunction would be denoted omega with a subscript of k. So, how do we determine if a function is an eigenfunction of a given operator, and how would we find the eigenvalue? Lucky for us, we would do both of these things simultaneously. So first off, we're going to write down our general eigenvalue relationship given to us by the third postulate of quantum mechanics. Operator eigenfunction equals eigenvalue times eigenfunction. Then we're going to particularize. We're going to plug in whatever operator we're given and the trial eigenfunction. By trial eigenfunction, I mean the function we're trying to see if it is an actual eigenfunction. And once we plug it in, we're going to apply the operator on the left side and simplify as much as we possibly can. And then we have to observe a little. If the left-hand side is now a constant multiplied by the eigenfunction, if this is a question, if it is, then the trial function is in fact an eigenfunction, and the constant we found is our eigenvalue. Or we could find no, the left-hand side is not a constant multiplied by the eigenfunction. And if it isn't, then our trial function is not an eigenfunction, and therefore we would say we can't define an eigenvalue. So now let's do an example and see if e to the 2ix is an eigenfunction of our momentum operator in one dimension, and if it is, let's find the eigenvalue. So first, from our third postulate of quantum mechanics, we're always going to write our eigenvalue relationship. So we have an operator applied to our eigenfunction is equal to our eigenvalue times our eigenfunction. Now let's plug in. So we plug in p of x, our one-dimensional momentum operator, and then we plug in our trial eigenfunction, e to the 2ix. From the second postulate of quantum mechanics, we know that our momentum operator is negative IH bar, and then the first derivative with respect to x. So now with that plugged in, we see the next thing we have to do is take the x derivative of e to the 2ix. Using our derivative rules, we get that that is 2I times e to the 2ix. From here, our derivatives are done. We just need to do a little bit of cleanup. So negative IH bar times 2I, we're going to get is negative 2H bar times I squared. And then we still have our e to the 2ix. But there's two things we note here. I squared is just negative 1. So our negative and our I squared cancel out, and we're left with just 2H bar. But also, e to the 2ix, that's our initial trial eigenfunction up here. So this is just our eigenfunction, or our potential eigenfunction, phi. So we could rewrite the left-hand side as 2h bar phi equals omega phi. This is great because this is exactly what we wanted. On the left-hand side, we have a constant times our trial eigenfunction. So since the left-hand side is a constant times our trial eigenfunction, we get that yes, phi is an eigenfunction of the momentum operator in one dimension. But more so, we see that for this relation to always be true, our eigenvalue omega must equal 2h bar. So we find that our eigenvalue is 2h bar. So let's try another example. Let's see if cosine kx is an eigenfunction of d dx, or our first derivative operator. So first off, we'll write our general relationship from the third postulate of quantum mechanics. Operator applied to eigenfunction is equal to a constant times our eigenfunction. And let's plug in. We know that omega, our operator, is d dx, and then our trial eigenfunction is cosine k of x. From here, let's differentiate to get k times negative sine of kx, or more simply written, negative k times sine of kx. And again, we're just holding the right-hand side the same. But from here, we can already say that phi is not an eigenfunction. So cosine of kx is not an eigenfunction of omega equals d dx. And to see that, let's plug in cosine k of x, our trial eigenfunction, for the phi on the right-hand side. And what this shows us is that negative k times sine of kx is equal to omega times cosine of kx. No amount of constants on the left-hand side will turn a sine into a cosine. So we can say with certainty that cosine k of x, again, is not an eigenfunction. Let's try one final example now. Is sine k of x an eigenfunction of our second derivative operator, d squared dx squared? And if so, what is the eigenvalue? So we're going to start as before with our eigenvalue relationship, and then plug in. So our operator is our second derivative, d squared dx squared, and our trial eigenfunction is sine of kx. And whenever I see a second derivative and I'm doing one of these problems, is I'm going to break that into two first derivatives, because the second derivative essentially is taking the first derivative twice. So we'll say that the second derivative is the derivative of sine kx. Taking the inside derivative, so this derivative here, we get k times cosine of kx. So now on our left-hand side, we still have to take another derivative, the derivative of k times cosine kx. And doing so gives us k times the derivative of cosine kx. You'll notice we just pulled the constant outside of the derivative. And then taking the derivative of cosine kx is negative k times sine of kx. Cleaning that up a little gives us negative k squared times sine of kx on the left-hand side. But we know that sine of kx, that's just our original eigenfunction, or trial eigenfunction, phi. So we could say that the left-hand side is negative k squared phi, which is equal to omega phi. This is perfect. This is what we want to see, because we have a constant times our trial eigenfunction is equal to an eigenvalue, a constant, times our eigenfunction. So from here, we could see that yes, phi is an eigenfunction, and more particularly, omega will be negative k squared, so negative k squared is our eigenvalue. That's all I have. Thank you so much for watching, and have a great day.